Welcome to another mini-series. Our previous series looked at generalized extreme value errors as a way to overcome the independence of irrelevant alternatives property of logit models. We saw how nested logit and other GEV error structures can overcome the limitations of the proportional substitution assumption that is built into logit models. Today, we're starting a new series on a different but equally important topic that is a limitation in logit models, and that is the assumption that everyone has the same preferences. This preference homogeneity assumption assumes that everyone would respond the same way to a price change or to some other change in the choice situation. And basically, this preference homogeneity assumption assumes that any differences in actual choices by different decision makers are due to purely idiosyncratic reasons. This creates unrealistic behavioral predictions. In reality, some consumers are price-sensitive bargain hunters, while other consumers prefer to pay a premium for luxury items. An example might be college students who choose their transportation decisions purely based on cost, compared to working professionals who choose their transportation decision in order to minimize the time spent in transit. Understanding preference heterogeneity is crucial for realistic behavioral forecasting, as well as for accurate welfare analysis and effective policy design. Today, we'll see how to move beyond one-size-fits-all preferences. One simple solution to this homogeneity problem is to simply add interaction terms into our model. So if we have a two-option commute model, consumers can go by bus or they can go by car. And let's just say that X is a dummy variable for if the person is a college student, and Z is the price. We can simply introduce preference heterogeneity on the price dimension by interacting Z with X. This new preference parameter gamma tilde would include the base price effect as well as a college student specific price effect. So we'll get two different numbers for gamma, and then from there we can use that to look at the differing price elasticity of demand for these two transport options. This is a very simple way to introduce preference heterogeneity, but it's unlikely to be fully satisfactory, and that's because a lot of different dimensions of preferences are unobserved to the data analyst. So in this case, we would need to interact our Z variable with something that's unobserved. One way that we can do this is to assume that the reference parameters, beta or gamma, vary across people. We can assume there's some distribution of gammas in the population. Maybe we assume it's normally distributed, and we call this the mixing distribution. And once we have this mixing distribution, we can integrate it out of our likelihood and estimate the different parameters of that mixing distribution. So we can get an average parameter and a standard deviation parameter for how sensitive people are to the price. We call these coefficients that are mixed random coefficients because they have a component that's drawn from a distribution that's random. And if we instead assume that the mixing distribution is discrete instead of continuous, then we call that a latent class model or a finite mixture model. So that is a little bit about how we can extend a basic logit model to have a little more realistic price response or whatever policy response that we're looking at. The important thing to keep in mind is that the generalized extreme value substitution effects are independent of these preference heterogeneity effects. So we could have both or neither or one or the other in our model, and each is going to make it more realistic in certain dimensions. The interaction term approach that we introduced at the start of the slides is really useful, and it's used a lot in a lot of different fields, but the limitation is that the preference heterogeneity that we're uncovering is only restricted to observable components of our population. The mixed logit, on the other hand, allows for those preferences, or that preference heterogeneity, to be based on unobservable components. So with the mixed logit model, you could have two people that are of identical demographics and income, and one of them still prefers the fancier brand of coffee than the other. And as we'll see in upcoming videos, adding this mixing distribution significantly complicates the computation And so we're going to need to come up with new ways of doing the estimation than just straight up log likelihood maximization. But before we get to these other estimation algorithms, we first need to think about identification, because identification always precedes estimation, as we learned in a prior video. So our next video will cover how we can use panel data to uncover this preference heterogeneity.